Okay, we have section 6.3, volumes. So just as area before was always positive, so is volume, and our attitudes towards finding it. So back in geometry, to find volume, we could have done area of the base times the height, okay, or area of the face times the height. And the faces usually in geometry remain consistent. And notice that each face, such as this or this or this, is parallel, or every face, every slice is parallel to that original base or the face. And this is where calculus comes in. What we're going to do is we're going to take the area of each of these slices and add them up to create a volume. So each slice is, if we're doing it parallel or perpendicular to the x-axis, each slice is going to have a width of dx. It's a difference of x, and we're going to add up all those slices and combine it to get a volume. Okay, so let's get started. Come on. I think it skipped a page. There we go. All right, so you can see these are really thick slices here. We're going to do a lot thinner because just like when we did Riemann sums, it's a lot easier to do by hand small or big chunks, but we're going to do small so we could get the most accurate volume possible. And you can read through this, but basically here's our big idea. We're going to take the integral from our a to b, whatever it happens to be, of the area. Area gives us 2 dimensions, and the dx gives us the 3rd dimension, and that's how we create volume. Okay, so I'm sure that you remember the volume of a sphere with the radius r is 4/3 pi r cubed, but we're going to show how you can derive that from calculus. All right, I'm going to try to draw this as accurate as possible. Oh, that's great, right? So we have this sphere, right? Yep, that looks great. It's definitely a 3-dimensional sphere. And so now, if you remember the equation of I need a pen here. The equation of a circle is x squared plus y squared equals r squared. Well, we're going to solve that for y instead. So the top half would be given by the square root of r squared minus x squared. And the bottom would be given by y equals negative square root of r squared minus x squared. Okay, so what we're going to be doing is we're going to be slicing this. We're going to say we take a slice right here. Our width is going to be dx. If we looked at it from the side, it's going to be a circle. Okay, and that would be our radius, and we're going to call it a disk, and you'll see why very soon. All right, and so how do you find the area of a disk? Well, that's just pi times the radius squared. And our radius in this case will be square root of r squared minus x squared. So we have the volume. I'm going to move my constant. I'll put it in the front first. All right, so now what are our bounds here? Well, we would be going from negative r to positive r as far as our x values. And then we have pi times the radius squared dx. I'm going to rewrite this. I'm going to pull that constant out to the front. We still have negative r to r. Square root of r squared minus x squared, quantity squared, just gives us r squared minus x squared dx. Okay, so if we take the antiderivative, okay, we get this. Plug in our values. What's that? R cubed minus r cubed over 3. And this one we would just change the signs. So then if I simplify that, I get r cubed plus r cubed, so that's 2r cubed. And then we get minus 2 thirds r cubed. So adding that together, we get 4 thirds r cubed and pi, so 4 thirds pi r cubed, which was our volume formula. So yay, calculus! Look, we're connecting to geometry now. Okay, so we're going to outline and specify this disk method for volumes. Anytime our cross sections are perpendicular to the axis of rotation, then we're going to call these things disks, because then maybe you can remember that we're going to do perpendicular. If what we're rotating around is perpendicular to each little slice, then we can use this perpendicular method. All right, let's try another one. Okay, so we have square root of x equals 1. We're going to rotate it, and the x-axis. Kind of missed that there. And we're going to take that slice, or this piece right here. We're going to take that piece, and we're going to rotate it around the x-axis. So let's see, we'll kind of make this shape, and that would be one slice. That'd be another slice. I'm trying to draw in 3 dimensions. It is pretty tough. Okay, so I don't know why that box is there. Okay, so then let's do this now. The area of each of these disks is pi times the radius squared. The radius in our case, we start there, or maybe it would be here, or maybe it'd be here, or here. So the radius is square root of x. We're rotating around the x-axis. These are perpendicular to our axis of rotation, so we can use this perpendicular method. Okay, so we start out, the volume is pi times the radius squared. And our x values, we're going from 0 to 1. So let me simplify that. That's x dx. That makes an antiderivative of 1/2 x squared. We're going from 1 to 0. So the volume is pi times 1/2 minus 0, which is just 1/2 pi. And so that is the perpendicular method. Now the next 3 problems, or the next 2 problems, are just more practice on the perpendicular method. All right, so we're going to, well, let's just try, see if we could fit both of them in here. So we have the region bounded by y equals 1. We have square root of x. And x equals 0. And we're rotating it this time around this line, y equals 1. Okay, so if I was going to rotate it, it would be kind of this like solid shape here, filled in. Okay, so it kind of would look like a solid funnel almost. So the area of each of those cross sections is going to be pi times the radius squared. The radius this time, though, well, I don't have a top function here, so I'm going to focus on this radius. The radius, I would be going from 1 to 0 here. I'd be going from 1 to x square root of x. I'd be going from 1 to square root of x, so it looks like it's 1 all the way down to square root of x. Okay, so now we set up our volume, pi times the radius squared. And our x values are from 0 to 1 again. Oh, Okay, I said radius squared, but I didn't write it, so I want to make sure I do that. We don't know any magic tricks to take the antiderivative of that, so I'm going to just multiply it out. I'm going to write x to the 1/2 instead of square root of x. Okay, take the antiderivative. Add 1 to the power, that would be 3/2, divide by the new power. So 4/3 x to the 3/2. And then 1/2 x squared, we're evaluating that from 0 to 1. So we get pi times 1 minus 4/3 plus 1/2 minus 0. All right, so 3/2 minus 4/3. That should be, I believe, pi over 6 for the end. Not so bad. Okay, so then how can I change this up? Okay, so we have this is this function. That's that function. It's that function, but this time we're rotating about the y-axis, so here. So it's actually going to be sliced this way. Okay, each little slice. So this time we have dy. Okay, that's what's different here. All right, so this could be our radius, or in this one, this could be our radius. So we're still going to do the area equals pi times the radius squared. We still have a disk. Okay, but now, now our radius is a little bit different because it has to do with these. Okay, it's going this way. So instead of being in terms of x, we're going to have it in terms of y. So this is the same as x equals the cube root of y, and that's what we're going to use here. Cube root of y. Okay, so if we set up our volume, pi times the radius squared, and this time we're going to be going from, we have to use y values here. So we're going from 0 all the way up to 8. So we get pi, I'm going to rewrite this as y to the 2/3. Now it's just simple antiderivative. Add 1 to the power. So that would be what, 5/3, divide by that new power. 3/5 y to the 5/3. And we're going from 0 to 8. All right, so the 8 to the 5/3, the cube root of 8 is 2, and 2 to the 5th is 32. 32 times 3 is 96/5 minus 0. So it looks like our volume is 96 pi over 5. Okay, I think that's good for this video.